Okay, once again, good evening to all. So we will start with the activities for the sessions for day 4 of the FDP on secure and intelligent systems on chip. So as Nalesh has explained to you yesterday, the 3 sessions from yesterday are on RISC-V and developing system on chip um, based on RISC-V ISA. So this talk is a continuation of yesterday's talk about acceleration. Accelerate adds on to describe verification also. So it's my privilege to welcome Babu, PS from founding engineer from Incore Semiconductors to talk about RISC-V ISA extensions, design and verification. To introduce Babu. Babu is a senior design engineer and one of the founding members of Incore Semiconductors, where he specializes in RISC-V based processor and accelerating SoC solutions. He has been actively working on optimizing data level parallelism through SIMD and bit manipulation instructions, driving the development of Incore's commercial grade Azurite, Calcite, and Chromite processor series. Babu has previously worked on India's pioneering Shakti program and collaborated with RISC-V bit manipulation technical group to enhance the E-class and C-class cores. He's an active contributor to the RISC-V open source community, working on, of course, test suites, simulators, and compilers and frameworks. He holds an MTech degree from QuizAd and strengthening the nation's open hardware ecosystem through mentorship in government-approved initiatives like the Design Linked Incentive DLI and Chip to Startup programs. He is our alumni, and it's my great privilege to welcome Babu to this particular FDP session. Over to you, Babu. You can start. Yes.
Thank you, ma'am. Welcome. I'll just share my screen and start. Can you acknowledge if the screen is visible, and shall I start?
Yes, you're audible and your screen is visible.
Okay, thanks. Good evening, everyone. Welcome to the session, RISC-V ISA extensions. So yesterday 2 sessions were part of the RISC-V, and this one will be dealing on to the extensions, which essentially means RISC-V is known to everyone as an ISA, right? Which is very familiar term, instruction set architecture, but I'm just abbreviating it. But this one will deal around what exactly does RISC-V do to an SoC, right? If I change my ISA, does that mean should I change my SoC, right? That's a fundamental question we will try to explore, and we'll take it a step. This design and verification itself is a quite big realm, and ISA extension itself adds more complexity. But I would like to try to keep it simple and minimal. I would be happy if this session is interactive. Questions are welcome. Please unmute yourself and ask question or put it in the chat box. Maybe I'm not able to see the chat box, but yeah, preferably ask the question anytime. That's open. And let's get started with the basic ISA refresher. Yeah. So what exactly is an ISA? So everybody knows that it's the hardware-software boundary, right? An ISA decides whether a software should work on a programmable hardware, right? So it sits between the hardware, as in processor or IO system usually. And here we are not defining what a memory interconnect and all that. We are just looking at very abstract sense and the digital design and the circuit design. And above the instructions architecture is what usually compilers are built. And if you look at this particular diagram, a compiler is definitely what most people use today to deal with an ISA. So just defining an ISA is not enough. You need a compiler support, and applications that runs on that compiler is needed. If a compiler doesn't exist, you can just write a simple assembly code and then still make it work on an ISA. And apart from this, an application on an operating system via the compiler to the ISA is the best approach that usually being taken because of the security and the modular reasons, right? So the software region and the hardware region are trying to be separate, or they can innovate independently as long as instruction architectures are available in the freest sense, right? So the usually other well-known ISAs are x86 and ARM. Other than that, we have PowerPC, which is now gaining a bit of attraction in their open source spectrum, but RISC-V has taken its own way to go forward. So yeah, RISC-V, some people who just say RISC-V, it's not, it's called RISC-V. It's the 5th iteration of the RISC series, right? So there are other iterations which is available in the Hennessy Patterson's RISC-V design book, but the history is not relevant, though RISC-V, it's not RISC-V. And it's a simple, which if you want to implement this instruction set architecture, it just has 40 instructions, nothing more, nothing less. And that's enough for you to start running something, right? It's as simple as that. And that's going to be stable. Those 40 instructions cannot become 41 or 39, right? So those instructions are stable. There is a set of stages before it can go through, before it's called stable, right? And it's modular for a reason. And that's modularity is what we are trying to talk about today, right? And this modularity is achieved using called extensions. And extensions are usually, you can think of like that extra performance improvement or the low power or the PPA requirements that you are trying to make out of a chip, right? That's usually achieved by using extensions. And none of this is done by one firm, right? It's a community activity. So a community tries to come up with something and then people come together to say what is good, what is bad. People are being critical about why it should be there, why it should not be there, what is the right approach to it, right? And when this is being told, it's still the specification. Nobody tries to tell you this is the exact way you should be doing it, right? So the implementation is still free enough. Anyone can do it, right? It doesn't matter academia, it's research, it's companies, whoever is free to understand the spec. It's a basic plain English to design specifications, right? And that leads to RTLs. And while I still say that you need to pass compliance test to say RISC-V compatible, right? What does that mean? So if I have 40 instructions, that 40 instructions should work the way it is intended to, right? And compliance cannot mean two things for two individuals, right? So there is a compliance test suite that's provided by the RISC-V itself, which you need to pass. It's called AICTE, Architectural Compatibility Compliance Test Suite. So you need to pass that to say this is RISC-V compatible. And obviously, as the competition increases, you get the better designs. As I go through the slides, in one of the bottom corners, you will see a QR code which actually points to the references that I picked from. And it's usually singular reference. Those QR codes would help you to explore more in the realms which I'm talking about. So the fundamental question that we are dealing in this whole SOCs, right? And we have boiled it down to a level called processor where RISC-V, right, sits. And now the fundamental question is, if you look at a simple SOC, right? I still say this is a simple SOC because it just has one interconnect, a memory that's connected via that, and an IO peripheral called UART, which actually is used to print characters or something. And there's a DMA to move the data across multiple peripherals. And there's a processor that's associated with the debug module for the processor and the platform level interrupt controller, right? This is like very basic. I'll call this as a ref SOC, okay, reference SOC. We'll have our whole session based on this particular reference SOC. And I would try to put, if I change a processor from, say, if that was an ARM or other specific ISAs out there, right, to RISC-V, does that change this whole scenario, right? Is it just this processor that's going to change? So let's get a bit of understanding on how an ISA works in the processor, right? I am just taking a 3-stage pipeline. This is equivalent to if you ever knew a 5-stage pipeline, right? A fetch, decode, execute, memory, and write back. And this is now toned down to 3. Fetch and decode happens in 1 stage, execute happens in 1 stage, and then memory access and write back happens in 1 stage, right? So you access an instruction from bus controller memory to the I-cache. It's preloaded in some sense, or a hit or miss mechanism. And then you fetch the instruction, you move towards execute, right? You fetch operands from your register file, because RISC mechanism itself works the way all the instructions are supposed to be worked from the memory, from the register file. Everything that's in the memory should be loaded in the register file before you try to access it, right? That's a RISC mechanism in the first place. And in line to that, so you access and perform, and then if there's a memory operation, you still do that, or you do a write back, right? And the Dcache supports your memory write backs, the load store mechanisms, right? And there is a basic trap flush if there's an exceptions, or the branch. If you figure out a branch, you need to move the PC, or you need to change the flow of execution, right? The change of the flow of execution is handled by this, right? And if you look at this whole picture, right, you can't see anywhere the RISC-V there, right? It's still agnostic. So this pipeline is agnostic to ISA. It's just RISC ISA. It doesn't mean it's RISC-V, right? Any RISC compatible ISA can be implemented with this particular mechanism. So a processor change in RISC-V ISA shouldn't make a difference, or should it, right? I want you to personally answer this question with yourself. So after going through 10 or 15 slides down the lane, there will be a same question again to ask the same question, like, does the ISA influence the outcomes of SOC, right? The whole idea of doing this exercise is how much an ISA influences SOC, okay, due to the extensions. So we'll now go back to the RISC-V basics. I just skimmed this slides for the reason that this could be most of them would be aware of this slides at least. So it usually starts with naming conventions, which is starts with RV, the RISC-V, and there will be a pound that represents one of this 32, 64, or 128, which represents your register file size. This is also known as xlen, okay, the width of the register file, and it also determines the size of your address. To map that to the C language, there's a variable called uint ptr, right? The pointer size. The pointer size depends on this, okay? And there's a mandatory extension that RISC-V always asks. It's I. And if you are, in going into deep embedded, which is like, ultra low power activities, then RISC-V also supports E. And the difference between the I and E extension is that I would only have 16 registers, right? X0 to X15, E would have X0 to X15, whereas I would have X0 to X31, right? There are 32 registers. So this whole RF is the makes difference, but both of them have the 40 instructions straight, okay? And this last part of the naming convention is the primary set of extensions. What does that mean? So primary extension means it's indicated by a single alphabet, A, B, C, D, right? So I have mentioned here one RV32 IMA. So RV32, which means xlen is 32. It's an integer subset. It has multiply sub extension. The multiply will have multiply and division as both, and then atomics, right? If there are subversions to it, right, then it will be represented with the P. So M extension 2.0 and A extension 2.1. Okay. So if there is a usual notation, you usually see this RV32 IMA, then whenever the architecture was out or the chip is taped out, that year is considered for the latest version of that particular extension. Okay. So the extensions keep undergoing revisions based on the need, right? That's what I meant as a stable, right? So if you are on 1.2, that means it's still stable. So you need to just be on 1.2. That's it. So if you are on implementing the newest RISC-V, it's preferable that you should go to 2.1, right? It's like updating your software, but not mandatorily. The last part, right? The mandatory part that's something important. So if you are implementing the latest, this is the first time that you're implementing, or if it's a new chip tape out, it's preferable to go with the latest versions of it. And these are case sensitive, and ordering of it is important. you can't keep IAM, right? The order is important. The IMA is the order. And the order, the semantics, and how that versioning and everything is available in this hyperlink. That's part of this QR code. Apart from this primary set of extensions, which is represented by a single alphabet character, the extensions can be represented, the last character called Z, right? Which is called additional standard extensions. What does it say? So it tries to tell which primary extension has a sub extension to it, right? I'm using two keywords here. Primary extension, which is represented by a singular alphabetic character, and there is a sub character, which is sub extension, which is part of the main character. So for example, if you look at here, this is XICSR. So it represents, it's an additional sub extension of I, right? It tries to operate on the CSRs, right? It's still part of the I extension. So you can still fully opt out of XICSR and then still implement RV32IM. That's still feasible, right? In the next slides, I will talk about what are the interdependencies between the extensions look like. And similarly, here is XIF and XI. So, for example, if you didn't have caches in your system, in the previous architecture diagram, if you looked at it, there's something called caches, right? So, if you didn't have a caches in the first place, you don't need FENSI, which means the instruction fetch mechanism doesn't need the cache clearance. So, XI FENSI can be ignored. So, you don't need this whole sub extension altogether. Okay. So, this is Z. Z is used for sub extensions. And if you have your own extension, right? So let's say I have my own compress mechanism as an instruction. So I can put that with an X, indicate with X. So X followed by, so for example, I have a unit called pbox, okay, which have my custom instructions to perform pack operations, right? Pack queue, those sort of operations. So I can name it like X pbox, right? Again, this is optional, this is custom, and there are slightly nuances on why when you go for custom extensions, there goes an incompatibility in the picture, right? While we tell that there's an incompatibility while using XPbox, you can still go ahead and run your software, or you can build your programs with just this part of the extension, because that's a standard, right? Until this part, it's a standard. So you can just still run with it. It's just that you can't use the custom instructions of the chip that's been using the X non-standard extensions or custom extensions. So these are some of the popular subsets. I for integer, E for the reduced integer, M for the multiply and division logic, A for the atomics, single precision, double precision, and floating point using the FDQ, bit manipulation with B, vector restrictions for V, and control status registers, XICSR, and instruction fence, right? This is XIF and XI. So I and E are mandatory, as I've been conveyed previously. So in M, if somebody doesn't want div, right? Why does somebody want a div? So div can be soft implemented. What does that mean? So you can use the combination of extensions or instructions between the I and M to implement your div, and new or the other compiler libraries already provide that, right? So if such an extension is needed, you can remove the M and keep ZMML, right? In the next slide, I will just talk about what that means. So I'm just trying to tell there are even simpler, or you can actually break down this MA, FDQ, BV extensions into further extensions, and that's what we call as sub extensions. Okay, and here we are going through some combinations to tell the interdependency of the instruction. So you can't put IMF. The reason being, F uses set of flags which tells you whether there's a NAND, whether there's an underflow, overflow. Right, this is a floating point operation which we are doing when using F. So you should definitely keep XICSR, right? You need control status registers to perform the F operation. So you can't run RV32IMF. You should use RV32IMF with XICSR, right? And then RV32IMD XICSR can't be used because a D requires F. That's again interdependency between the primary extensions, and the correct way is to use IMFD, right? So this order of semantics, order of notations, right? The sequence, the order of sequence, both of them is relevant, and it's case sensitive too. You can't keep ZICSR all in caps, right? Either way. So these are certain restrictions on the ISA, and this has been forcefully adopted by everyone. So this doesn't, it stays universal. apart from Z and X, there's a alphabet that's separate. It's called G. G stands for general purpose, and this is what that extension looks like. So whenever you see RB32G, right, that means it's RB32 IMAFD XICSR XIFNSI, right? So now here, if you look at it, there are 5 primary extensions, IM, AFD, 5 primary extensions, 2 sub extensions, XICSR and XIFNSI, right? And there are 4 privilege modes, right? The highest is the machine and the lowest is the user, right? If it's a deep embedded system, you just need to only implement machine. If it's a not so deep embedded but has a user privileges, you go for machine and user, or you go for machine, user and supervisor if you're using operating system. If you are going into virtual machines or server levels, you will have all 4 of them, right? That's about ISA subsets. Now we will talk about RISC-V with respect to SOC. Basically, a typical SOC will have, this is a pretty hot take, I understand that. There are other components to SOC, but these are the primary components when you look from the RISC-V perspective, right? The memory, the IO, the interconnect, the fabric or known as fabric, and the processor, right? So the processor is what you are seeing here, right? And what I'm trying to convey from this slide is how does a simple pipeline like this would vary as you add extensions to it, right? If you add a primary extension, what would happen, right? If you add integer, if you add reduced integer, if you add a floating point, if you add a vector, how does it look like? So I'm just taking one portion of the pipeline, which actually is a sub portion of your SOC, which is the RISC-V, and I'm trying to look from the perspective of how does it vary for E. So E will have X and Y 16 registers, right? And the moment I implement I, it becomes 32, just double of it, right? And if I go for implementing floating points, F, B, or Q, then it actually increases. Observe the difference that XLN is only for the non-floating point operations, right? Whereas FLN is still dependent on this FDQ. So if F, it is 32-bit wide, D means 64, Q means 128. And this also follows the format IEEE 754, right? So which means that you now have 64 registers, but the top half of the 30 registers is of different FLN, right? So just by changing or adding your extensions mean, you are increasing your performance, but you are aware of your PPA trade-offs, right? And then there is a beast called vector, which has its own register file altogether, right? So I just didn't mention any of the dimensions, specifically for a reason that this can vary up to VLAN 128 all the way to 4096, and recently they have introduced that to shrink it to 32. But there comes a combinations which will have LML, there is SCWs. There are a lot of combinations that can make this implementation pretty dependent upon the architect, right? So they just only tell we need V0 to V31 32 registers of VLAN byte. That's it. And they don't tell you how to implement it, right? The VLAN has no meaning in the sense like XLAN or the FLAN, right? That's the reason why I didn't have any specification on the width of your register, right? If you are banking it, the registers would make a difference. If you are non-banking it, if you are going for a register dynamic mechanisms. So depending upon the microarchitecture perspective, the implementation would differ. So the whole gist of the slide is that as you add extensions, there are certain ways that performance improves, so does your PPA trade-offs will differ, right? So the understanding of that would actually deepen without, how can I improve performance without adding too much cost? And that's the reason why we have additional standard extensions, right? So if you look at, there are almost close to 40 sub extensions out there, right? All of them would, since that's so huge a list, I didn't completely put that here. But if you scan this QR code, you can figure out how many extensions and what are their versions, right? So if you look at, I'm just trying to point out the way it's represented, right? Like I told it previously, the first character after the Z would represent the primary alphabet to which this belongs to. And each of them serves its own purpose, right? and going through all of them as part of this ISA design and verification session wouldn't make any sense. So I would try to limit myself into going to very briefly tell how to add an instruction to the core, right? That's pretty much popularly asked question. How can I add a custom instruction, right? A custom instruction never doesn't mean you have to put that in the X, right? That's the ideal way to do it. But say, for example, you want to implement a counter, right? A counter that just says how many ads you got into the pipe, right? You can think it that way, right? So let's take that as an example and then revisit our session. So I just told, right? So there are 42 close to sub extensions, and I was talking always about the ISA, right? Which always touches your pipe, and there are things that actually changes when you bring in RISC-V. And if you look at here, I just closed in on debug and trace and the PLIC. And if you look at, there is an interconnection between that. So if PLIC is supposed to tell your RISC-V core there's an interrupt, now you need to stall, service it, and come back, right? And you need a mechanism for that. And not all mechanisms are same. So ARM uses something called NVIC, and RISC-V supports something called PLIC, and that's those, whatever I'm terming words like PLIC, that's actually non-ISA specifications. We call that non-ISA specifications. So PLIC tells you how to deal with interrupts, right? How many targets do you have? How many priorities do you have? Does you have a gateway, right? Those sort of specifications are dealt in the PLIC. So technically, if you're designing an SoC around RISC-V, there are slight changes, not all the changes, but the way the processor is gonna deal with certain things, right? So those things will change. Similarly for debug and trace. So PLIC will never gonna hurt your host software. What I mean by host. So if you ever work with an Arduino, your Arduino is usually connected to your x86 PC, likely, right? Unless you have Surface laptop which has ARM, but usually x86 PC is used, right? So that's called host, right? That host has to connect to your board or the chip that's been taped out, or the board which you bought in of the RISC-V. So which is actually done using something called debug and trace, right? So this has now communicated to some architecture which is different than what you're designing, right? So, and that has to communicate it. So there are multiple components that go through this, right? And I'll be dealing that as part of this session. And what I just talked about is what's called non-ISA specifications, right? Even though we just keep RISC-V, there are certain things in the non-ISA segments that need to be part of your RISC-V so that RISC-V works flawless, right? So this left portion of it is called non-ISA, and the pipeline things that we are going to talk about, right? Adding a custom instruction can be thought like ISA part of it. So we'll first go in one part of the ISA. We look at the design and verification aspect of it, and then after that we will take a non-ISA specification, look at the design and verification aspect of it, and close the session. Okay. So coming to the design session, I just talked about right now. We should put a counter as a custom instruction to the pipe, right? So let's assume this whole pipeline is already having RB32I, right? The 40 instructions that has memory operations that can do via memory access, operations like add, shift, those operations can be done via the register files or the logical operations, and the fence operations that can be done using the your instruction fetch level itself, right? So this is a typical pipe, and if you want to add an instruction, right, to this pipe, what are the probable choices? I would like this to be interactive, but I'm keeping that question and answer to myself. So the first better or the fastest approach is to take an input from the buffer, because we have already an instruction that's decoded, assuming that decoded, and you have a stage, right, a parallel to your execution. So you need to have a sort of a decode mechanism which tells you, just bypass from your execute and put that via your new block that I have introduced, right? So one of the fundamental reasons why this is hesitated, but not in open source, but in closed source community, is that pipe is a key part of your timing closures, right? Most of the times, if you take critical path of your typical RISC-V core, it would be somewhere between either the fetch decode stage or in the execute stage or at the decache stage, right? So it goes from memory to Dcache to L2, or if you don't have an L2, it goes towards a bus controller, right? So the longest path happens in one of these stages. So unless you are aware of keeping that instruction, but still not to tweak the timing aspect of it, right? This should be doable. And the only catch is that now the register file have an extra access port, right? This is a separate module altogether. So this register file in itself, if you look at it that way, it's a complex, slightly complex memory structure that sits within your core, right? And this is like, you can think of even faster than your SRAM, right? So the cells are actually highly modified for this fast access reads and writes, right? And every additional reads or writes to this register file port will add cost onto your PPS, right? The area cost will increase and the timing cost will increase. And you should understand or appreciate the way that we are still at the microarchitecture level and we are thinking about the circuit level things, right? A small change at microarchitecture can still have a bigger trade-off that you have to make at the circuit levels. So it's pretty much doable, but you need to understand the trade-offs. So let's say if this is not feasible or if this is costliest option, what else do we have, right? The option is to connect towards the write back session. What does it do? So you now fetch and decode your instruction, bypass it through your op fetch stage, right? You don't do any operation on here, but you still try to access your register files from the existing data paths, right? So an op fetch, while bypassing, can fetch your operands, right, past your pipeline buffer. So memory access is anyway supposed to do things, right? As part of the memory access, if it's a memory operation, if it is not, you offload that to your particular module or unit, and then this particular arrow mark, right, bidirectional arrow, points you to certain protocols, right? So you can't just directly connect to memory or write back stage and expect it to done, right? So first fundamental question is, how long does this operation take? If it's 1 cycle, is it 2 cycle? Is it eternity? Or do you tell me whenever this is complete, right? Those sort of nuanced details are needed. So there's a handshake that explicitly exists, and there are multiple protocols that you could use, right? There's a protocol called XF, the cross interfaces. This is coming from Pulp, that's an open source core, and there's a ROCC that coming from Rocket. And you can have your own custom protocol also, depending if how much control you have on your whole pipe, right? So it tries to tell you how much you can do a transaction between your core as an offloaded unit, right? And now, if that's just the register file, that's okay. But what if you need memory access also? For example, take a matrix multiplier, right? You can't take all the inputs of your matrix multiplier from the register file. That's pretty, charging, or there'll be a lot of load stores that should happen into a register file before you need to do it. So now the easiest option is to have a separate path to your Dcache, right? So this seems deemingly simple, but this opens a bigger problem called physical memory protection, right? What if a certain user program is not allowed to read that location, right? If you have a chip that's, recently all the Windows laptops are coming with TPM modules, right? Protection modules. So those protection modules are not supposed to be read by everybody, right? It's supposed to be something that's at boot level, right? If you're not in that level, if you're not in that mode, you're not supposed to read that particular memory, and you should block it, right? And RISC-V gives you a thing called PMPs, physical memory protection, and that tells you these are the things that you need to take care of before you go and access the memory, right? And that's usually part of your memory access, right? Before it goes to Dcache, right? So if it's a missing a Dcache, you just go to reach out to controller. So there are multiple variants of this implementation of PMP. Some will keep at bus controller to Dcache level, so Dcache never sees it, or you keep at the memory access to the Dcache level, or you keep it to the memory access. That again depends on the microarchitecture, which we are not delving into. But in the offloaded module, if you're gonna read it, it's the offloaded module needs to be trusted now, right? The root of trust is now slightly changed to notion that, okay, this third-party IP that I'm gonna bring in is now trusted to say it will never access this particular address. It's like trust me, bro protocol, which doesn't work. So the usual method or mechanism is to pass it back to memory access, right? And memory access will now say, either it says denied or it says accepted. It's a two-way response, yes or no. And it goes and uses its existing protocol mechanism, which is like safe, to perform your mem access operations, right? If this is also taxing on the PPAs, the final approach is to connect that to the bus, right? And this way, the latency is going to be big. But if this is a long doing operation, right? So for example, the mat multiplication, right? If it's a wide 512 cross 128 sort of multiplication, right? You just take its input, you handshake it, and then you take its output at some point, and you have a memory map saying that, you write to this address, say start the operation, and you can keep it interrupt, or, you keep a polling mechanism, and then look out for a status register and see, if this is done, right? This pretty much is not taxing, but the cost is on the latency, right? So now every access, or the first access, will go to the bus controller, and then the operation kicks off. And once the operation is done, you need to tell it back to the bus controller. And the best strategy usually is this one, unless you have that micro instruction that is supposed to be worked out, right? So that way you don't disturb your pipes, what called critical timing, or area metrics, but still can have the best out of the design. So these are the primarily ways to add your custom instruction to the design, right? I didn't dealt with specifics because each approach is unique, right? That's what RISC-V provides you to do. But the more the understanding of the pipe or the implementation, the better you can add your custom instruction to the module or to the whole pipe, right? So with that, we will talk about the next in the sequence of the design of adding a custom instruction, and that's compilers, right? So you added the whole new instruction, but if nobody uses it, there's no point, right? And compilers are usually the dreading, scared thing for most of the designers looking at that way. They would only love to see the assembly code and then get away with it. But that's not a right approach. The reason being, compilers are usually translating language to language, if you look at it that way. It tries to compile from the C language to your assembly, from CPP to the Python to the Rust, right? If you really don't understand the semantics of how it's doing, you likely gonna, you can make it better microarchitecture if you understand the semantics that goes through, right? How does an optimization of a compiler would make a difference? How does a new flag that you introduced into your compiler makes a difference, right? Because a compiler to memory or the assembly, not even assembly, the instructions itself is a long path, right? So if you look at here, there are multiple stages. I'm not delving into all of them because this session is not meant for that. But trying to tell you that there's from the source code to your machine code, there are a lot of things that happens in between. And if not deeply understanding it, a higher level understanding of things would actually make a difference. And specifically, if you are into custom instructions, that would actually make more difference, right? Because if you look at it, here is simple thing called swap, right? You can technically say it in four character swap, right? You just know you have to put from X to Y and Y to X. But if you write it in C code, it looks like this. If you put that into the just I extension, it looks like this, right? You have loads and stores and sequence. And if you take a longest operation in a typical I subset, loads would be in the first place, right? So loads take the longest because it goes all the way from your, first of all, you should reach your last stage or the memory access stage. And then I'm talking about the in-order course, and you should go to the D-cache, it has a miss, and then it goes to a bus controller. It has to go through multiple fabrics to reach to the memory, right? It takes the longest operation of all. So these 4 instructions could actually eat up most of your cycle than these 2, right? And the last one is a taxing one, the JLR, right? Jump and link return. So if you look at this particular sequence itself, it should give you a pretty much idea on can I write a better code to get with this, right? That doesn't mean microarchitecture should go and write a better code. It's about how to squeeze the last level performance from your codes, right? That's what usually benchmarks are, right? So there are people who usually do this benchmarks absolutely perfect, but when you are running in real world, it runs damn hot. And you can see that mostly in architectures out there. Benchmarks run very nice, but the moment you start using the device, it just gets hot. So this actually starts from people writing any language program that traverses through the compiler that just goes to assembly programming language, right? And this is the only stage I have put it here, right? And there is an assembler. Usually the device drivers are written in assembly because PAXMD is not a big forte of compilers, right? If you want to have multiple data with a single instruction type operations, assemblers are the best way to approach. And most of the big names that you can think of still do that way because libraries are not something that you touch every day, right? So you assume that that's there and then you go ahead with it. For example, convolution operation, right? You can write your own assembly based sequence and the convolution operation is fixed. All you need to do is the parameters change, right? What the convolution operation parameters change. Rest of things will remain same. And that goes to linker. Linker is mostly like, how your program is designed, or how does your structure of a program looks like. For example, in RISC-V, the stack usually grows upwards, right? Can you literally make your stack failure known to your pipe, right? What does a stack failure look like? So as you keep growing upwards, you would write up into a region, or you try to put that stack push into a region where it's not supposed to be there. It's like a data region, right? So at that point, it's technically if you say that's a read-only region, right? Now there will be a bus access fault, and you definitely know when a stack happens, you end up in a bus fault, and that would tell you, okay, there's a stack failure, right? So intelligent or a smart linker scripts, writing a smart linker script would help you to actually keep your program sane, right? And eventually what you get out of that is hex that you can turn into any of the little endian, big endian formats as necessary, and then load it into your boards, right? So this is a small slide that tells you the importance of a compiler that deals with your pipe, right? And then comes the verification. So the same way where we use the specification to tell the implementation, the same specification should be used for verification collaterals, right? So it should be like both are independent jobs. So if you start looking for the implementation and then you do it, it's like it's not gonna be effective, right? So the implementation defined and microarchitecture defined specifications are used, and the parameters, the more the parameters in your design, the complexity of your verification slightly goes up, right? And the levels of verifications can be divided into 3 types. One is unit level, just like how it's represented here. It's either a mul or div. For example, I just had a mul div operation just implemented. I can just verify that, right? It's part of the unit level verification. And there's a core level verification. For example, the M extension altogether, right? How does when you integrate that to pipe, right? The M extension sits with your pipe, and then now you are doing it with multiple other instructions, and how does it work? And then finally, your system level, at SOC level. So if you have all the components put together, does that work well, right? So there are 3 levels of verifications, and we go through each one of it. Before we go through that, there are essentially 5 stages to it. One is planning, and then developing test bench, eventually reaching into the verification, right? It's a formal or the simulation, whichever it is. Take the coverage metrics, which says how much of the state space have you covered, and then say sign off. Sign off essentially means that what version of it you have worked it, and then it's done. So I'm taking the CocoDB as my unit level verification because Python is something pretty much popular. Nothing with SVUVMs. SVUVM is the most used industry standard, but PyUVM is still taking its own pace to be there as another standard, right? So you have a test sequence which tells you, and again I'll deal with what the test sequence looks like. And there's a driver which drives you to the reference model via the input monitor and to the DUT, which you are trying to multiplication, division, branch predictor, whatever it is. And there's an output monitor. From the reference model, you try to take your output, wait until your observed output or whatever the DUT output is there. You try to take it to the scoreboard and then say pass or fail. This is pretty simple mechanism from the looks of it, right? And each of them has its own libraries from the CocoDB library itself, or CocoDB folks. So it can tell you what the input monitor looks like, driver looks like, output monitor. All you need to tell is like, these are my signals that needs to be do as part of the design, right? And you can have your sequences also controlled. You can have your coverage metrics controlled, all of them, right? So this is COCO-TB, and this mechanism would differ based on what type of UVM you're approaching, right? You're using SVUVM, you're using EUVM, right? Based on the language, based on the units that you're using. So commercial IPs usually provide these models as is. You just need to use that. In case of COCO-TB, you are free to tweak it as you want, right? There are multiple other ways where you can do unit level verification. And unit level verification gives you a confidence only on that particular unit that it works, right? And then comes the block level or the sock level verification. And both of them have some amount of commonality. So if you look here, I just kept a pipe, right? And a gray color box, which I meant to be like sock, right? The easiest way to compare this sort of simulations is to have an instruction level simulator. So I'll introduce what Spike is. So Spike is actually instruction level simulator specifically for RISC-V, which has a basic test SOC, right? Which will generate certain log dumps, right? As it goes through the running your program as part of that's given by the test loader. So you run it on your DUT, which may be in any of the favorite tools that you use regularly, and your simulator, you have a log dump, you compare both of them, right? And then the comparison would lead you to the scoreboard and the test pass fail reports, right? So the challenge is that the instruction level simulator and the design, right? Both of them has to be close enough, or simulation dumps that generate should be close enough, right? You should have that part of your design. So this is another aspect of your verification at higher abstractions, right? The higher the abstraction you go, the complex the verification you have to take it or deal with, right? And there are now more tools that's making it easy to do that. So I have talked about instruction level simulator as a Spike, right? And there is a newer mechanism coming up, or it's pretty much used. It's called RISC-V SAIL. SAIL is a language that's explicitly used to define the semantics of an ISA, right? What do I mean by semantics? So if I'm talking about the I-type instruction, what is an I-type? So I-type is like instruction with immediate operands, right? So it tells you there's a source operand which is supposed to be operated along with immediate and put that to destination register. That's it. So this is a plain English that can be used to generate collaterals like this, right? If you had a custom instruction that say does modulo operation, right? Is that modulo operation based on RS1 and RS2, or is it based on RS1 and immediate, right? Those are two variants now. So to avoid this ambiguity, you just define this as a plain English and then ask this particular SAIL tool to generate formal specification for that, right? And you use that formal specification to as a reference model to run your pipe, unit level model or the soft core level tests, right? So this can do a type checking. You can use this to generate or see emulation models, have coverage tests, right? So you give this and then now the tool knows what all the state space needs to cover to get the coverage metrics out, right? It has automatic instruction sequence test. So this is pretty important if you are dealing with memories, right? Memory instruction, for example, the xi FENSI. So if you are doing FENSI for 5 times, that doesn't make a difference. But if you are moving from instruction A to instruction B, right, which is independent, are you using xi FENSI and does it operate the same way it is supposed to do? So that can be only detected using something called instruction sequence tests, right? So these all can be done using SAIL language, right? So there are slightly hiccups while using this in commercial aspect, unlike the COCO-TB, but now it's pretty well oiled so that most of the ratified extensions are available in the RISC-V SAIL, right? Unratified, there is still a nice tutorial out there again to do how to do it. And now we'll talk about the Spike IC simulator, which is actually golden model for quite some time. I mean, from the days of the introduction to RISC-V, right? RISC-V started along with the Spike, if you want to put it that way, right? So Spike is a golden model still used by everyone, and it's not a cycles accurate, which means even your load stores are single cycle for that matter of fact, right? But there are caches, but that's a bare simulator, and your internal delays can be simulated. It doesn't mean, so we have to tell my cache miss latency is 14, which means it will stall for 14 cycles just before it gives you the IO response. That's it. It doesn't emulate or the behavior exactly like a Gem5 tool, right? The advantage of why using Spike is Linux kernel using the Berkeley bootloader BBL. So most of SOC level boot up can be verified with the Spike, right? You feed the same kernel images to your core as well as the Spike and see the log dumps are pretty huge. I'm not going to deny it. It turns into close to 400 odd GBs, but you can still do it, right? If you want to do instruction by instruction comparison, which is not something that people would recommend, but I'm trying to tell how far extent you can go with the Linux kernel with the Spike ISA. So we have a rough model. Now we'll talk about the test sequence, the test loader part. There are two ways to do it. One is directed tests, right? These are the primary ways to do directed tests, which is ACT, which is a compatibility test suite. This talks about RISC-V ARC test, which is given by RISC-V consortium to tell you if your core is compliant with the RISC-V specifications. And there is RISC-V test, which is self-checking. It sort of looks like this. So it's just a lot of macros and your code, right? So if you look at it, what here we are trying to do is we are trying to test this add a instruction, right? I'm trying to test if my test data, which is 41, when it's added to 42, I just store that to result section, right? The D word here in the result section. And then I'll just try to compare with the branch instruction, right? This is sort of self-test. If the branch instruction fails, it fails. So you have a fail macro that runs and then you go to the code ending, right? Or else if you pass it, then you have a RB test pass and then end it, right? So this is a sequence mechanism to do a self-test in your core pipeline to tell if the pipe works or not, right? Self-test it. So even before you go with architectural compatibility test suite, you start with RISC-V test. So if this passes, then there's highly likely then you can go for other tests. If this one doesn't pass, then there's a serious problem that you need to solve, right? And the directory structure is pretty much here. I mean, you can just go ahead to this directory to see how it looks like, but this is how it is. So it says XLAN, the privilege mode it uses, user, machine, hypervisor, supervisor, and the extension, right? The primary extensions again. And now comes the random tests. It's necessary to check your state space, right? And you can't be fully random because there are a lot of illegal combinations that could happen, right? You don't want too many illegal combinations, but you want the test to be random. And there comes a term called constraints, right? And there are 3 open source suites. One from Shakti project itself. It's called AIPG. The other one is called, okay, Shakti project uses PyEnv, which is Python interface environment for the underlying infrastructure to run the AIPG test, the RISC-V torture, and the microtest. RISC-V torture uses the Java, microtest uses Ruby platform. So if you look at it, there is a bit of things. You use Python, you use Java, you use Ruby to test your same core, and there comes the problem of multiple things just to verify one core, right? And there is a test framework to tell RISC-V config if it is IM, what are the legal combinations? If I did IMA FDC, what are the legal combinations, right? So the RISC-V config will actually tell you what are the legal combinations, illegal combinations, and those stuff, and it will automatically help the other tools to generate the right instruction sequences and instruction tests, right? So to amalgamate all this, we have a thing called River Core. This is a platform from Incore itself. Incore, as part of this open source projects, we did this. What it just takes is it's fully on Python. Whether you do it on Java, it's Ruby, doesn't matter. As long as all the necessities are satisfied, if you use a River Core, it should do it, right? And this is commercially used also. What you technically do is you try to pre-process and the post-process along with the configurations set rightly, and then you feed it to the framework and it will do it. And the framework almost looks like this. If you remember my 5-stage definition of test plan to the test generation, running formal verification, and then the coverage metrics, sign off, right? So this whole pipe can be done using this whole verification framework. It all starts with one single config file, right? This tells you what are the tests you want, what is your targets gonna deal with or not deal with, where should the target should search for the libraries that it wants, right? All the details can be contained in one config file, right? And then that's used to generate your tests, which can have pre and post operations on your generator test, right? Should you trim out something? Should you add something after you generate test, right? Those sort of things. So, for example, there are certain tests which are very specific, it can only write to certain signature regions, right? It's called signature region itself. So that's part of your generation test. It's part of the post-generation things, right? You generate a test and say there is a signature region like this, just write to it, right? And you get a test list, which will have all the collaterals. And this will be driven into the reference model, which can be your spike, sail, or your custom commercial simulation models, or your DUTs. It could be a rocket, CBA6, or a custom pipeline, which can be going through all this. So each of these blocks is a hook, right? Python hooks. So if you want to control at the init point, if you want to control the build point, so if you don't control it, it just runs. If you want to control it, you can take the hook controls and then take it. It uses a PyTest mechanism, by the way. So you have an elaborated coverage report for that, and then it compares the log and puts in a pass-fail report with the time off, right? So that sign off will give you this report. Okay, how much of confidence do you have on the pipe you have just designed, right? So this framework will help you to run all the tests you can think of, right? Whether it's a APG, microtest, or whichever test you can think of. So all things happen at here, APG, test, torture, whatever, and you can still use the same framework for everything. And now we'll come to non-ISA. What it technically does is to, if you have ever saw the Arduino screen, this is how it looks like when you go for a debugging slot, right? You would have used the play pause button. There is a step, there's a loop, reset, and all that. So this essential functionality is achieved by using called debug module, right? The debug module that's connected to the ISA. And these are the pretty functionalities: resetting, halting, resuming if it's halted, reading the registers, right? You can stepping through the programs, right? So all these operations are done via the debugger. So people or the core won't be realized without a debugger if that's that's very well known it works, right? So if you know the pipe works, if you know the soft works, and if you're pretty confident, you can opt out debugger. But most of the times you keep the debugger there and then you authenticate it with a block, right? I'll talk about what that authentication means, right? So no bad actor can use the debug to void your security, right? So debug is an essential part of your SOC, and that connects to your core and controls your core. Now we'll talk about how the control happens, right? When I told, so if you're looking at in this particular picture, right? So when you're doing stepping, what exactly happens? You just are supposed to do one instruction, or you just do the whole function that you see it. So even though when you see it's a digital write, it's just a function. A digital write would have multiple other instructions in it. So should you step by instruction or should you step by that function, right? Those are things that gets micro details that you go through. But before we go through that, this is another popular IDE which is using, so it's other than Arduino, there's a popular IDE that uses the same debug module history. So you have the registers, you have disassembly and all that. So we'll talk a bit about architecture again, right? This is other specification again from the RISC-V. This is non-ISA specification, right? So debugger, this is a GDB new debugger that comes from the new tools. This usually, the debug host is usually x86PC. Usually, it could differ if you're using Mac or Surface laptops and all that. But the essential point is that the debugger is RISC-V compatible one. This is RISC-V 64 unknown elf GDB. That's how the tool name binary looks like. And this connects to something called OpenOCD, which is like a translator for your debugger. Okay, and OpenOCD is a universal tool. It connects to a lot of debug transport hardware. The debug transport hardware essentially here mean the JTAG link, J-link you use, or if you ever looked at FPGA connected via USB port, right? So that USB port actually goes to something called debug transport module. It's called FTDH usually, right? So that's one popular example for the debug transport module. That debug transport hardware will convert the USB serial signals into your transport module, right? You connect to that transport module. So please look at the names DTM, DMI, DM, which I'll use it often in the subsequent slides, right? So the USB to JTAG probe will convert the signals into the DTM, right? And via the DMI interface, at this point, it's totally serialized for the debug module, and it's in a RISC-V platform. Okay, so the connection ends here, right? So this is the only interface that exists, and you go to the debug module. So all this dotted lines represent multiples of this particular debug module, right? So there can be multiple debug modules, multiple DTMs, multiple cores, right? Multiple hearts, right? So you can control multiple hearts with the same debugger again, right? And in the debug also, there are multiple options for bus access. You can have it optional, a program buffer. A program buffer is like, a small memory where you can execute your custom code, which is not at all part of your loaded code, right? You remember the compiler to loaded health, right? So you can run a code which is irrelevant to that using the program buffer. That's what I meant when a bad actor can use a debug module if it's not protected or authenticated. So a system bus to access your whole bus peripheral. So your debug module sits as a bus master on the interconnect, right? So it's a future rich, but the spec is very limited, right? So all this solid rectangles are what's supposed to be implemented, and we'll just talk about that and proc buff also, right? So this is just outlining, whatever I just told, right? So it just gives the necessary implementation details. That's it. So how many GPRs do you have? What is the area bound regions of your SOC, right? You give the X2 by region and that's done, right? So it's the basic minimal things that you need. So you don't need to even give beyond the GPRs, right? So if you have only 16 registers and that's the only access that you need to give as part of your debug module. So there's a bare minimum specification. The biggest ask from the debug module is you are supposed to halt your heart, right? You're supposed to be able to stop it. When I mean stop, it doesn't mean you should turn it off, right? That's a fundamental question. So how can you halt without gating it, right? So the usual options that people can think of is power gating or the clock gating. So if you turn off the clock, if you turn off the power, that's easy way to halt. But a register file and those things will hurt the business, right? So how can you do the halting operation, right? So that's the gist of the next slides. So there are optional part of it, which I'm gonna skim it in the country of time. So there are 127 registers. Again, it's huge, but these are the primary two registers that makes a difference. But other registers are as important. Here, if you look at it, this is a control. This takes a control of all the hearts in your code, right? And the primary signals that you need to look at is DM active, which says if the debug mode is active in the first place, right? And this one will drive the reset signal. Reset signal is very special in the debug module, which essentially means debug module won't get reset, but every other peripheral gets reset, right? And in most of the SOCs, reset is very unique, right? They'll have a sequence of resets, right? You can't reset everything at once and then expect it to work, right? You shut down one and then you shut down the next and the next. There's a sequence of shutdown and there's a sequence of power on. So this NDM reset is capable or aware of the controls, or should be aware of the controls as part of your implementation. And these are most of selection window, which is like a hard selection and the number of the heart, right? And then it tells you whether you are in a reset state, you're in resume state, or in a halt state, right? What the operation do you want, right? So these are the control signals, and there are unique equivalent mapping signals here. So it tells you whether all of them are unavailable, all of them are running, all of them are hard stopped or not. Is it resumed, right? If it resumed, did it acknowledge, right? Those sort of signals do we have it here. And as we look at the previous slide, there are three mechanisms that you can do it. One is abstract command, one is proc buff, and the other is sysbus, right? Proc buff and sysbus are optional. Abstract commands is mandatory. And in that abstract commands, access register is only mandatory. So quick access and access memory command isn't, right? Access memory is still needed, but you can limit that to a bare minimum, right? Which essentially means the same PMP restrictions that I have applied there, right? So if the PMP restrictions are applicable, then it's not supposed to read it. So that's applicable to the access memory command also. And this is how the access register command looks like. So there's a 16-bit register that's available to tell which register are you interested in. Are you interested in the CSRs? Are you interested in the GPRs, floating point registers, or the non-standard extension registers, right? So the control side registers can be probed also with the GPRs using the access register command. And this will, if it is a write, you do write to your GPRs. You can also do write to the GPR or your CSRs, right? So while I keep telling all this, so okay. So the proc buff is an optional. You technically what you do is you write a piece of code into the proc buff, which is actually 64-bit wide usually, or you can reduce it to 4-byte, doesn't matter. It's a flexible as part of the implementation. So you write something and then say post execution. So what it does is like now pipeline, instead of fetching from your bus controller, it fetches from this proc buff and then executes it. right? And once the execution is done, you go for busy. Now the fundamental question is, when you're executing something like that, right? If you kept a faulty instruction in that prog buff, what's gonna do, right? The answer to that is it goes to again something called trap handler, which is a standard mechanism in RISC-V. If you encounter something illegal, you go to that location, right? It's set by MTVEC. But the only catch is that it won't go to a trap handler that's set by your user or the machine mode. It goes to a trap handler set by a new mode called debug mode, right? So the gist is that when you are running in a debug, everybody or the whole pipe knows that you are in something called DM, which is called debug mode, right? I'll talk about that in the next slide. So prog buff can be implemented in a way that's suitable. Again, there's nobody that's enforcing how to implement it. Prog buff can be done with RAM, or you can have your own register files, or you can totally opt it out with the simplest of possible ways to do it, right? So as part of the CSRs, there are three, actually four. One of them is missed. Yes, okay. So there's a three to four registers. Actually, fourth one is there, something called DRET. It's missed. So the first register is DCSR. It tells you, are you in a debug mode in the first place, right? And tells what's the action is gonna be, right? And e-break is a special instruction which tells you if there is a no debug mode, it's an illegal instruction, right? And it's a soft illegal instruction, which means you can just bypass it, right? You get an e-break, you go to trap handler and say PC +4, because e-break is not harmful one, at least. So if there is a debug module, then e-break will go and halt your code, right? And then DPC tells you, by the point the debugger came in, what was the piece that you're executing it, right? So this holds it. So when you're resuming, you take from the DPC and execute it. And dscratch space is used to tell the debug module. I think there is a program, if you are running it, you can hold those variables in the DCSR or the scratch space, not CSR. And there's a DRET which tells you now exit out of that routine, right? Just like how you have return instruction of your function, this DRET is just exclusively for the debug return function, DRET, okay? And your heart mode is in the debugger mode, which these are the functionalities of it. It's generally acts like an M mode. It's like a machine mode, the highest privilege possible. And debugger is actually one step ahead of it, which means it can fully fledged, like it can fully give the control, take the control over the pipe, or it's supposed to, right? So unless it's a long standing operation, say for example, if your load store operation is taking 15-20 cycles, so your debugger is waiting for that to complete, just for that, right? So now there is a question like, why shouldn't I stop before that? Or why should I stop between that, right? So these things are something that's implementation defined. So I can do my load store access however I want. I can do it in a single cycle if I'm implementing TCMs. But if I have a cache and a long sequence of things, then I can take it longer. So now debug module is supposed to tell where exactly, how exactly, and what exactly to do, right? So those are the stuff you need to know. It's not a longer thing. So that's what I meant when you need to understand your pipe fully before you go ahead with this. So if you're implementing your pipe, I would prefer somebody else in parallel to understand this pipe and implement the debug module, right? So that's a handshake approach you usually take. So on the debug side, you need to implement halt, right? And when we say halt, it's essentially equivalent to stopping your code. But the catch is that all your state space variables should be seen. Your memories should be available, your register should be available, your control status register should be available, your GPRs, floating point registers, everything should be visible, right? But yet your core seems to be halted, just like you have a breakpoint and then it comes and halts there, right? Something like that. And one of the finest approaches with the software is using something called parking loop. What it does is, like, there's a sequence of instructions where you keep running, right? And this sequence of instructions is capable of figuring out how to do it, right? And this mechanism is explained in the debug specification itself. And these are the 5 states that you need to understand. That's it. So if you are running this parking loop with these 5 states, so it goes and reads from the debug ROM halted to understand if it's a halted state or in a resumed state and what it's supposed to do, right? Should it run an abstract command, or should it go, if it's a resume, should it go to halt? If it's a halt, should it go to resume, right? Those sort of sequence on the ROM flags. And where is abstract command? It needs to get it from. And if there's an exception, right? This exception could happen for any reason, by the way, and how to handle that gracefully, right? These 5 things are captured in the memory mapped IO, and this is pretty much shown to the parking loop while you load this. And there's a specific name for this called debug ROM, right? This is a smaller ROM that sits in your debug that's doing this parking activity. So you can get rid of this and can have your own implementation. But this is one way of implementing in the design side for the debug module on the debugger side. And on the core side, what you need to do is once you get the debugger request, you set the debug mode state bit, which is like, I told you, right? Other than a machine privilege, machine user, hypervisor, supervisor privileges, 4 modes. So there's a 5th mode called debug module. This is exclusive state, right? So this has all privileges like your machine mode, right? So this state is set. So the pipe essentially knows all the stages the pipe knows that it's in the debug state. So now if an exception happens during that, you again jump to this exception loop, right? It fetches from here. And if it receives an interrupt, right? You look closer here. I'm saying that interrupt from the DM, right? So a debugger module is supposed to give a non-maskable or a maskable sort of an interrupt, which is quintessential to enter the part loop in the first place, right? If you mask this bit, now the debugger has no more significance, right? And I told, debugger has an authentication thing in the backend, right? So if you look at the debug register, right, you can set your authentication and see here. If this bit is unset, right, authenticated, this interrupt is never gonna trigger the core, right? So authenticated is as important. And how does this authentication being done? It's another module for that. But in the gist, it's like your OpenOCD is now capable of understanding, okay, this is the debugger module. I know how to deal with it, right? And then they do a handshake like a key RSA protocols and then say like, this is done. So the key authentication mechanism sets this bit and you can't set it on the whims and fancies using the DM control. And it has to happen the way it has to happen via the OpenOCD during its initialization phase. Right, now we are onto the final stages. So verification. Now debug module spans across your core, it talks to your interconnect, it talks to your pipeline, it talks to the sort of an interrupt like PLIC, right? It spans across multiple things. How exactly can you verify? It's not going to be easy, probably, but if you are first implementing the bare minimum, it's doable, right? One of the prominent things that you could do with verification is to test the basic using the OpenOCD, right? OpenOCD is supposed to talk with DTM, which has a RISC-V support, all right? The J-Link or most of the things are ISA agnostic, either way. And the GDB is already available there as a tool from the new community altogether. And these are the first 3 things that you tested. Is it capable of running from the halt to heart, right? If it's a heart that's running should be halted and the other way around. And can you single step it, right? Can you run instruction by instruction? So an instruction runs, it goes for a halt. And then when I give the next trigger, it goes for executing the other instruction. So these are the 3 simple tests that you can do via the OpenOCD. And the accessing to GPRs is the next subsequent test that you do as part of the abstract commands. So once this is done, I think pretty much you have control over your debug module design, right? What works and what doesn't work. So when I told this is still on the non-core side, right? Which essentially means from the bus to your debugger module. Now, how does a core and the debugger module talks about, right? So there is a sophisticated test that are present part of the RISC-V test suite itself. So you saw that self-checking test, right? So there's a specific thing called SDEXT, which is a debugger extension. So external debugger. So those tests will tell you whether it's compliant to the basic minimum that's required by the RISC-V. So your RISC-V debug specifications are there too. So this is how you go on with the debug module verification. So, okay, I'm already going into time. So the trace is essentially trying to figure out if you are running your core in the field and it failed somehow, the somehow is unknown, uncertain, right? Can you capture it, right? And the trace actually supports it. So debug and trace is usually 2 separate specifications. Trace is still optional. But what you do is a heart will tell you these are the instructions that are retired, and trace will generate a packets. There are 2 mechanisms. One is called efficient trace, ETrace. Other is Nexus, and it uses this trace packet to tell where are you in the ELF, right? So you need to tell. I mean, the ELF should be available to both of them. So if this ELF is if you don't know what is running in your heart in the first place, there's no usage of this trace model in the first place. But if you know what the ELF is, what your program is, then you can use this trace packet, decode it, and compare it with the ELF and say, look, okay, this is where it went and this is where it didn't went, right? And you can actually pinpoint your mechanism when your chip is running in the field, right? It's not in the lab per se, but it's most of the time used in the critical systems to figure out why it failed, right? So that's a trace. In the lieu of time, I'm just taking it out. The final part of, so this whole thing we are talking about is SOC, right? Secure SOC. And Incore has its built own tool called SOCGen, which is a SOC generator. What it tries to tell, or what it tries to do is, it tries to take a specification. Where do you want to put your UART? Where's the PLS should go? What is the type of core you want, right? What is the type of extensions do you want, right? Do you need a fabrics that is light powered or no powered too much, right? So those specifications can be told in the SOC, and then we automate it and then gets the collaterals for it, right? This happens in very short span than a typical SOC development in SOC development cycles, right? It tries to reduce it, but I keep this to bare minimum. So such a tool exists today at Incore to come from the specification to the RTLs as quick as we can, right? So that marks towards the end of the session. So since this is an open standard, right? RISC-V is an open standard, and if you have interest in any of this layers, application all the way to digital design, I'm not going to tell circuit design because circuit design is independent of the ISA. But if you have interest along this, there are multiple technical groups, special interest groups, and the horizontal steering committees, which will talk about the ISAs. And if you are expertise in one of these areas, right, whether it be DSP, AML, or those sort of things, so you can actually start contributing it to make the community better, implementations better. The competition is gonna make things better for future. Yeah, with that I wind up and I'll open up to the questions. Thank you.
Thank you, Babu. Are there any questions? Okay, so we wait for the questions. In between, I would just want to thank Babu for giving an overview of, I know it's a very broad topic, but giving an overview of how you can modify, design for design RV30, that is RISC-V pipeline, modify the RISC-V pipeline to add new instructions. So yesterday's talk, we had touched upon topics like adding custom instructions to accelerate something. So in this talk, you have added upon it to show how you can actually do it. So so I had talked about doing this at top level to improve application performance. So this talk has shown how to actually do it. So thank you for presenting that. And followed by an overview of how you can, what do you mean by verification? How do you verify it using simulation, using Python framework, and then how you can actually verify in the design itself, that is adding debug features and trace features. These are the options. You have given an overview of it. Anybody who wants to do more can connect with him or can have a pointer of what exactly that person has to do. So thank you very much, Babu. I'm hoping that that people have at least are aware of some of these keywords that they should look for when they are planning to work in this area. Thank you, Babu, very much. Thank you very much for your support and this presentation. Okay, so I think we'll wind up this session.
Okay, sure.
There are any questions? Okay. No, there are no questions. So the presentation will be shared, right? So if they need anything, I'll definitely.